for absolute values? Okay. So we're going to talk about getting an absolute value function from a graph. So let's say we have some absolute value function. Maybe it looks like this. Let's say this is some point maybe 1, 5, and this is some point maybe 0, 3. Sound okay so far? All right, so if I want to write an absolute value function, I remember that every absolute value function can be written in this form. So that's going to be my plan, is I just want to write some absolute value function that fits this form. So I'm going to go to my graph now, and right away, I can fill in some of the A, B, H, and K just by looking at the graph. So the thing I need to remember from this is that the vertex is my H and K. So in this case, that's 1, 5. Everybody okay there? All right. What remains now is to determine my A and B. If you remember, though, when we do something like this, we're always going to either assume that A equals 1. Can we just stop talking about the bug, please? Put it away, throw it away, squish it, whatever. But let's stop paying attention to that and pay attention to math. That either A is going to be 1 or B is going to be 1. So the way that we remember which one is which, we're going to assume that A equals 1 when the graph opens up, and we're going to assume B equals 1 when the graph opens down. So in this situation, if I look at my graph, which one do I have? Yeah, the graph is opening down. Okay with that so far? So now what I have is, and I guess I can just forget about the B since we're just multiplying by 1, right? Okay to hear? Erica? Okay, I'm not finished with this problem yet. So I'll call on you next, and we can certainly talk about that next. That's okay, because we still need to figure out what A is, right? So that's the last thing I need to do. Notice there was some piece of information here in the beginning that we haven't yet used. So I'm going to use that. That is a X and a Y, right? So if I go back down here, I can plug those in for X and Y. And that'll give me an equation that I can solve. And I get that A is -2. Okay there, Rachel? Okay. So now that I have that, I can write my final answer. That's talking about quadratic functions. I mean, it's the exact same thing. So I have some vertex and some point. So I'm going to do the exact same thing. So I'll just plug in 0 and 3 for my X and Y, plug in 1 and 2 for my H and K, and -1 squared is just 1, so I just dropped it. I get a is 1. So I'd say g of x then is x minus 1 squared plus 2. Okay with that? Okay. Erica, you were trying to ask me something earlier. Let's go back to that. So let's say we have something like this. Actually, I'm going to make that 7, make our lives a little bit easier. So something like this is what you're asking about, right? Okay? So to solve this, we'll just start using our usual solving algorithm and subtract 1 from both sides, and then divide both sides by 3. And now, since our absolute value is less than or equal to a positive value, we can split these. And when I split, you have to remember that when we negate the right-hand side over here, we need to make sure we flip the inequality also. And now we can just solve each of these inequalities separately. And what I need to decide in between these, should that word be and or? So to do that, I'm just going to graph each one of these two inequalities on a number line. So x is less than or equal to 4. That's this one. And x is greater than or equal to 0 is that one. Since they are pointing towards each other, that is the and situation. Okay with that? So you're talking about graphing a function? Okay. So let's say we have something like this. If I want to graph this, how many points do I need to graph an absolute value function? 3 is the answer. And one of those 3 points must be the vertex. And which one of these 3 points in my table needs to be the vertex? Where does it need to go, though? Okay, so the vertex needs to go in the middle, and the values for the vertex are? -3 and -1. So far, so good, Erica? Okay. Now, for the two x values, the x value left of the vertex, I have to pick an x that's less than -3. I could pick -4, for example. And then to the right of the vertex, I need to pick an x that's bigger than -3. I could pick -2, for example. Are those the only x's I could pick? No, there's lots of different possibilities, right? Now to find the y-coordinate, all I'm going to do is plug my x into the y spot and simplify. Okay, so far? And now, I remember here that because I've picked these x values so that they're the same distance from the vertex, when I do that, I get the other y value for free. It should be exactly the same. So now I just need to plot these points. So I have it looks something like this. Is that what you're asking about, Erica? Yeah? Okay. Atala? So you are talking about solving by graphing? Is that right? So if I had something like absolute value less than or equal to some number, I might graph the absolute value part, and I might graph the number part. So if I do that, it's either I'm talking about the part that's below the number, or I might be talking about the part of the absolute value that's above the number. Right? What I'm going to do to make that decision is look at my inequality. So since this is less than, we read as below. So I'm looking about where the absolute value is below the number. That's the yellow section here. So what I'm going to do is I'm just going to trace down and find those y values. Maybe that's -3 and maybe that's +6. Okay, there. So my x's then are greater than or equal to -3, and they are less than or equal to +6. Alternatively, you could write this as, this way, or you could write it as like an interval on your number line. So any of those ways to write that solution set would be fine. If this instead had been like a greater than symbol, that would mean the above parts. So it would be talking about the blue parts over here. So that's going to be where x is less than or equal to -3, or where x is greater than or equal to 6. And you could write that as an interval also instead, like -infinity to -3, like that stuff, union, +6 to +infinity. And that would be an okay way to represent your answer either. Would I give one preference over another on the test or whatever? No, as long as you have an acceptable formatted answer. I'm okay with any of the formats. I'll let you use what's most comfortable to you. Connor?
So you can put like any inequality equation
Well, no. I mean, what the absolute value inequality looks like, absolute value equation looks like, will matter where the v is, right? Whether it's pointing up or pointing down, or where the location is, and what the number is will make, give you a different horizontal line. But they all kind of look like this. I just tried to draw something general.
So we would have to get into that one table and graph it and then figure it out.
Unless I gave you the picture to start with, and then you're just reading something off the graph. But yeah, I mean, you could certainly generate your own graph and then do it, or you could, if I gave you the graph, then you're just reading information off of the picture then. Ferris?
Okay, so you told us this question again that would start with 3 absolute value rates. Yeah. So with that one, if you have defined like the final solution that you're given, if you would make it into a segmentation one, like because you're given you got those numbers, if you put it into like something you were talking about.
Yeah, I mean, that's fine. You could do any of those things are okay. Yeah.
And then my a side question for the first one when you're doing
The first one.
yeah, the very first one that you're doing.
So that, okay.
Yes.
Okay. What's next? Allison? That is what I'm referring to. Yeah, so if we have an absolute value function in this form, we can think about it as a transformation of its parent function, which is just the absolute value of x. And the way we can describe that is just using your descriptors that you memorized in Module 1 about what the a, b, h, and k do. So for example, if we had, say, something like this, and I want to describe this, I just start by identifying the value for a, b, h, and k, just using this general form up here. So my value for a is -2. My value for b is 3. It's the reciprocal. My value for h is -1. Remember, there's a minus sign here, so it's the opposite. And then my value for k is -4. Did I already write it? Okay. So once I've done that, I can then use that criteria that you memorized to describe the transformation. So when I look at A can do, I have to check two things with A. I need to see if A is negative, which it is. So negative A means we are, yep, reflecting in the x-axis. And I also have to check the magnitude of A. Since the magnitude of A is bigger than 1, we have a vertical stretch. And then we have to do the same thing with B. The B, though, I notice is positive. So what does that mean it does? Nothing, right? What would it do if it was negative? Yeah, reflect in the y-axis. I notice the B values, the magnitude of the B is bigger than 1. So that tells me I have a horizontal stretch. Good. And my H value is negative, so that tells me left 1 unit. And my K value is negative, so that tells me down 4 units. So that's basically all I would need to do for something like that. So again, nothing too terribly difficult, but it did require that I had those criteria still remembered. And again, we'll see that probably just about every single function we talk about. This A, B, H, and K thing will come back up over and over and over again. So it's probably a good idea to memorize it. I'm just saying. Connor? Doing the exact same thing we did before, where you make a 3-point XY table. Yep. So just make a 3-point XY table, just like we did in the previous example. Ferris?
Okay, so for why is that in so many equations we use this y table, but some we just kind of like think, okay, well this has a vertical stretch, you know, there's that side. So you know what the vertical vertex is. So if you just put that down on the graph, it's like, let's see what this equation. Like the first one, you just kind of like base it off of.
So the difference is between the command graph versus sketch. So graph, you want actual points. Sketch, you just want general shape. So if you just want a general shape, you can just kind of like, oh, I know what the parent function does. It's going to go, you know, left 1, down, or left 1, down 4. We have these 2 stretches and a reflection. So it's going to be like, you know, like down here somewhere. And that's enough, right? So if the command says graph, I need actual ordered pairs and actual points, and I'm looking for precision, versus sketch, where if you sometimes just kind of knowing-ish what's going on will be enough. Okay? Okay. So, what's next here, folks? Allison? Okay. So in the bike lab, or for the bike questions, what I'm going to do is I'm going to basically give you like made up data of, some bicycle. Like it'll be the same made up data or same data that you collected. So maybe this bicycle has 2 gears at the pedal, and maybe it has 3 gears at the rear axle. And maybe this is my table of observed wheel revs per 1 pedal rev. And you might have, like, I don't know, I'm just going to make up some numbers. So you might have something like this that I give you. And then the other data you collected were the teeths. So maybe we have, kind of the same shaped table, but this time I'm giving you the teeths. Actually, let's make sure it's just 20. That's probably going to make my life easier. 20. A2 maybe is 15. And then A3 maybe is 10. So this would be, so the teeth are here. What I'd ask you to be filling in this table are called the gear ratios. So do you remember how we got that calculation from the lab? It's just the crank divided by the axle, right? So we'd have 1.25, nope, that's 1.3, I think. And then that's 2. And then down here we have, that's 3 over 2, so that's 1.5. And then we have 2, and then we have 3. And I would have to tell you the diameter of the wheel in there somewhere, so maybe I tell you that's 27 inches. So the other major calculation you did was how fast in pedal revs per minute do you have to pedal to go, say, I don't know, like 40 miles per hour. And there are really kind of 2 ways that you could do something like this, and they're both essentially like the same way. In the lab, we suggested you could figure out the conversion factor for 1 pedal rev equals how many inches. And then you could multiply that by figuring out, in this case, 40 miles per hour is equal to so many inches per minute. And if you situate those 2 ratios the correct way, you can multiply them together to spit out pedal revs per minute. I think maybe the easier way is to just kind of go directly there. So if you just start with 40 miles per hour, we can just do unit conversions all the way down until we end up in pedal revs per minute, kind of accomplish the same thing just in one set of equations rather than breaking it up into like 3 separate calculations. So if I want to do that, let's start by converting hours to minutes. So I know 1 hour is 60 minutes. And now I'm going to work on converting miles into pedal revs. So I know 1 mile is 5,280 feet. and I know that 1 foot is 12 inches, and I know that 27 pi inches is 1 wheel rev. Where in the world is 27 pi coming from? What's the circumference, right, of the wheel? And then I know that up in these tables above, I have a conversion from wheel revs to 1 pedal rev. If I wanted to do this in the most efficient way possible, which one of the two tables would I look at, the top one or the bottom one? The bottom one. And which ratio would I select from the bottom one? The highest one, in this case, 3, right? Table, yeah. So that would be 3. And then it's just a matter of observing here that we did this correctly. So hours cancels with hours, miles cancels with miles, feet with feet, inches with inches, wheel rev with wheel rev, and we're left with a unit of pedal rev per minute. So at that point, it's just a matter of kind of multiplying and dividing things out to get the number to go along with that. So you should be able to reproduce either or both of these two set types of calculations. You should be able to calculate gear ratios. You should be able to calculate how fast you need to pedal to go a certain speed. It doesn't matter which one of the two techniques you use for me, as long as it's clear as to kind of what it is that you're doing. So if you're using technique 1, you just kind of explain to me what you're doing and show that the units all match up when you do the multiplication at the end. Or if you're using unit or method 2, again, if you just line everything up so that everything cancels out correctly, that's fine also. Doesn't matter to me which one of the two you use. You should be able to, though, also answer kind of general questions about the bike lab. Like if I asked you to identify the most efficient speed off of the table, or if I asked you to order the gears from most efficient to least efficient, or to describe the difference between the numbers in the two tables, or these sorts of things that are just kind of like general, like, do you understand kind of what the numbers in this bike lab mean kind of in relation back to a bicycle sort of thing. Allison? Yeah, exactly. Yeah, so you're just ordering them from biggest to smallest, basically, or whatever. Yep, that's all you need to do. Ferris?
So the circumference, you found that by using the
Right. Yep. Connor? Yeah, so if we're talking about domain and range for absolute value functions, there's kind of two different ways you could do that. So, like, you could take and look at some graph. So, let's say this is my absolute value function. Go ahead. Yeah, go ahead. Yep. I saw you were having some kind of problem. So, let's do the domain first. Oops. I want a different color there. So the domain is about which values? The x's. So if I start at the negative x's and I track up, do I run into the function? I sure do. And if I move along the x-axis and keep tracking up or down, I keep running into the function, even when I get out to positive infinity. So I can say the domain is, negative infinity to positive infinity. And then we'll do the same thing with the range. We'll start down here at negative infinity, but when I track left or right, notice I don't run into the function for any y values until I get to here, and then every y value afterwards I run into the function, right? So the range goes from -2, the y value of the vertex, to positive infinity. So you can do it by just looking at the picture. If you're given just, say, a function or whatever, we can figure out the domain and range just by looking at the equation without even having to graph it, though. So the domain is always all real numbers. For all absolute value functions, you can just, that's going to be true. The range, though, this has two possibilities, and the possibilities depend on, or how do you figure it out, is you have to, it depends on the A value. So if A is negative, we're going to do one thing, and if A is positive, it's going to be a different thing. Okay? So if A is negative, the graph opens down, right? So that means we're going to be starting at negative infinity and going up to that y-coordinate of the vertex. If A is positive, it opens up, so we're going to start at the y-coordinate of the vertex, and we're going to go up to positive infinity. So you could do it that way also, where if you're given the equation, you don't even need to necessarily have to graph it. You can just use the value for k and a and figure out the range, because the domain is always going to be all real numbers. Yeah, no problem. Who's next? Allison. Sure. So, let's just do an example. Allison has a cell phone. She pays, maybe we should say each month, she pays a $15 activation fee and 8 cents per text. Write a linear function to describe her monthly bill. Everybody okay with this situation? Okay. Since it's a linear equation, we know that we're going to write something in the form y equals mx plus b. And let's think about what the x and y are going to represent in this equation. So y is going to be the, what are we trying to describe? Monthly bill. So like that's the dollars for the bill, right? And that depends on what quantity? Well, the number of texts, right? That's the thing that's going to cause the bill to change. Everybody okay with that idea? Okay. So to write this equation, then, we need to find the value for m and a value for b. So remember that the b value, this is the y-intercept. This is the point where the x-coordinate is 0, and the y-coordinate will be b then, right? So to figure this out, we ask ourselves, what is the bill if 0 texts are sent? And the answer to that should be $15. Therefore, my b value is 15. Everybody's okay with that idea? Okay. The next thing we need to do is worry about what the slope is. So the slope is a rate. It's the change in y over the change in x, or in this case, the change in dollars over the change in text. Now, if I remember back to my story problem, I was given something like that, right? 8 cents per text. That's exactly the quantity that I'm given there, right? So the word per is a good indicator that that's going to give me my slope. So there's that. So I can say then my equation is this. Everybody happy there? Now that we've written that, I could ask things about, or questions about, or that might require using this, such as, if Allison's last bill was $17, how many texts did she send? So, what am I going to do with this information? The $17 is which value? That's a y value. So I can just say 17 is equal to 0.08x plus 15. And I can solve for x. Please. So I found that Allison sent 25 texts. Get off your phone, Allison, is what the moral of this story is. I'm just kidding. 25 texts in a month probably isn't very much. Who sent more than 25 texts today already? Rachel, thanks for being honest. Stop using your phone at school. All right. We just have a few minutes left. Are there any other questions before we call it a wraps? Okay.